In this section of our course, we're going to take a closer look into the fuel that we're putting into our engines, understanding the properties of the fuel and how those properties affect how our engines operate, how much power we get out of them. We'll look at the efficiency of the engine and so forth. So that's where we're heading now. And the way we're going to break this down is we'll first look at just some basic properties of the fuel and how those properties are going to impact the engine. We're going to look at how we can do some estimation of energy performance if we put different fuels in our engine, so have an idea of how these different fuels are going to affect our engine performance. And then we'll spend a little bit of time going back into those ignition properties, octane and cetane again. We've talked about those, but we're going to tear that a little bit deeper and really make sure we understand that. And then finally, we're going to look at the efficiency of this engine, so ultimately trying to figure out how much of that fuel that goes into the engine is coming out as useful work. That's my efficiency. So that's the way we're going to tear that off or tear this up into 4 sections. So let's begin looking at properties. So what are some of the key properties? And we'll look at each one of these in more detail as we go. So the first property, the first 2 properties there are very closely related that we're going to look at is the energy content of the fuel. How much energy is in that fuel that I'm putting into the engine, and that's going to tell me about the potential amount of power that I can get out of the engine and so forth. So we're going to do that, the energy content and the energy density. I'll explain the difference between those two. We also have to keep in mind the physical density of a fuel, and the physical density is just how much a certain unit of volume weighs. So it's mass per unit volume or weight per unit volume. So how many pounds in a gallon of fuel, or how many kilonewtons in a liter of fuel, and so forth. So that's the unit that I'm looking at there in terms of density. Again, the ignition properties we're going to look at, and we'll look at that one specifically in octane and cetane. And we also have to keep in mind the flowability. So we talk about the viscosity of a fuel, how easily it flows, and we'll see with some of these fuels that they can be really affected by by temperature, and so that can be a big deal for us in terms of fuel supply management and so forth. So those are some of the key properties, and we could make a list way long and really dive into this a lot of detail, but these are the key things that we need to make sure we have our head wrapped around that have a direct impact on how our engines are going to operate. So let's look at this energy content a little bit deeper, and we'll look at units and so forth. Now, most of us are familiar, at least basically, with the concept of a calorie. So we've heard that word. We've talked about calories. The official definition of a calorie is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. So that's its official definition. So where have we seen that? We've seen this in our food products, right? So when you pick up your favorite soda or whatever kind of food that you're eating, we have an idea that there's some calories associated with that. So that calories is the amount of energy in that. So this particular can has 170 calories. So I know that my body, this is the fuel that we're putting in my body. I need so many calories to do stuff. So to lift things, to move, to do all that kind of stuff, I've got to have a certain amount of calories. Now, we know that in our body, if I put too many calories in my body and I don't have the output to go with it, I'm going to start adding some fat or whatever deposits in my body. So there's a balance that we need to think about, the amount of energy or the amount of fuel. So you can think of this as fuel going into my body, how much of that fuel is going in, and how much work am I doing in terms of an output, and how is that balance going on? Am I storing anything up? So that's the same concept, that basic concept. Instead of looking at calories in the food, we're going to be looking at the amount of energy that's in our fuel. Now, we rarely talk about calories when it comes to fuel. What we're typically talk about and our typical units is a joule. So we don't talk much about calories. Now, there is actually a conversion from calories to joule. So 1 calorie is equal to 4.1868 joules of energy. So when we're looking at fuels, we're typically looking at joules, and that's a direct conversion, so we can just convert that number if we want to. Why do we use joules? What are the units of joules? The unit of a joule is a Newton meter. So that same concept of energy that we talked about early on, where it uses the same units of torque, and now we can start thinking about power. It's like, wow, if I have the joules, the amount of joules or Newton meters of energy that's in my fuel, then I know a time in there, Newton meter per second, that gets me to power. So how much of that fuel is being consumed by that engine and how much energy is in that fuel that's being consumed, that gives me my power. So that's the concept that we're going after. So most of the time when we're talking about fuels, we're going to be using this unit of a joule. So a joule is a Newton meter. Okay, so that's what we use in the SI units, is a joule. Now, English units are a little bit different. We have this thing called a BTU. And a BTU stands for a British Thermal Unit. British Thermal Unit. Okay, so that's a unit that we use, and we actually do use that. So similar to a calorie, it's the heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. So if I had a pound of water, that's how much energy or heat energy, the thermal energy would take to raise that temperature of that 1 pound of water. So that's a British thermal unit. And we do see this reported in our fuels in terms of energy content. So we use this unit. So now we're going to need to know a conversion. So when we start doing some calculations with this, we need to understand a conversion. So the key conversion is that 1 BTU is equal to 778 foot-pounds. So there we go. So we got Newton meters up here, which we know factors into our power equation really easily if I can put the time into it. Down here I've got, 778 foot-pounds. Foot-pounds, yeah, so I can take foot-pounds if I know foot-pounds per second. I have that conversion. It was 550 or something like that to get me to horsepower, so I can do that. So these are the units that we're going to be working with. So 1 BTU is 778 foot-pounds. That'll be a conversion. It'll be available on equation sheet or something like that. It's a conversion that you can look up. So it is a definition. Okay? So that's energy. That's the content of the fuel. Again, thinking about this as kind of like potential energy. And, we had this concept, if I can lift a weight. So if I lift a weight a certain distance, I have a certain weight that I lift, and I lift it a certain difference. So many pounds that I lift so many feet. It has potential energy. If I drop it, it has that pound-foot of energy. So my chemical energy, the energy in my fuel and the chemicals, is measured the same kind of way. So even though it's not that physical moving of things, it's measured in a Newton meter or a foot-pound. So that's how much energy that I have in there. So those are the units, the fundamental units of energy. Now, we talk about energy density because this is energy, 100, whatever numbers. So if we go back to my soda can, I have so much energy in there, 170 calories, but this is 170 calories per 12-ounce can, which is what this can is. So I need to know those same kind of units for my fuel. So what I'm going to use is an energy density. And we could do this a couple different ways. We can measure this on a volume basis, so I would have a BTU per gallon is typically what I would see in English units, a BTU per gallon. In SI units, it would be a kilojoule, and we generally measure these in kilojoules because a joule is really small, so 1,000 joules, so many thousand joules per liter. So again, that's the energy per unit volume. The other way that we'll often measure this is on a mass basis. So I might have a BTU per pound of fuel. So I might do so many BTUs per pound of gasoline or diesel fuel or whatever. Likewise, in the SI units, I would have kilojoules per kilogram. So it would be a kilogram of mass that I would measure that. So this is on a mass basis. Now, can I get from one to the other? There's a real easy way to convert from one to the other, from a mass basis to a weight basis. And here's where the density comes into play. So this is the density of the fuel. And the density, again, is how much a certain volume of fuel weighs. So the density in the English unit might be so many pounds per gallon. All right, so it'll be pounds per gallon in the English system. In SI units, it would be kilograms per liter. So we would use one of those units, so pounds per gallon. So if I got BTUs per gallon and I have pounds per gallon, I can do my units cancellation thing and I can come up with BTUs per pound. Okay, so this is a property, the physical density of the fuel is a property of that fuel that I'm going to need to know, and that goes through this. Okay, so key things here, again, joules and BTUs in terms of energy, how we can convert them to foot-pounds, and I'll show you a little bit later how we take that to power then by looking at how much of that fuel, what's the flow rate of that fuel, how much fuel is that engine consuming. That'll tell me how much power, equivalent power of fuel that engine is consuming. So that's energy density. That's a key thing. We're going to come back. We're going to use that a lot. But let's dig into some of these properties and start putting some numbers on these and see what the numbers look like. So let's look at typical fuels for a spark ignition engine. Okay, again, we can put a lot of different kinds of fuels in engines. The most common that we're going to be talking about is either gasoline or some blend with ethanol. But again, it could be a lot of different kind of fuels. So like in a forklift, we use propane, or we could have liquid natural gas, or we could have methane. We could have a lot of different kinds of fuels that we burn in a spark ignition engine. But these are the key that we'll look at with some properties with them. So, and I've listed some of those physical properties so that we have some numbers on it. And we're going to use these numbers in some calculations here in a little bit. So the energy density in BTUs per gallon, so gasoline's 115,000. Ethanol over here, pure ethanol, 76,000. So we see that ethanol does not have as much energy in it per gallon. So it's got a lot less energy per gallon. In parentheses down here, I have the SI units for us. So if we, when we do some calculations, if we need those units, they're going to be there. I also have the typical densities of these fuels here. We don't use that as much, but at least we have that we know we can work with of what those are. And I also show the octane rating. So if we look at these fuels, gasoline has a much higher energy content, 115,000 versus 76,000 of ethanol. But look at the octane difference, and we'll come back and hit this again. But octane for gasoline, anywhere from 87 to 95 that you buy at the fuel pump. Ethanol is 117, much higher octane. And we've already talked a little bit about, okay, why do performance racing engines use ethanol? It's a lower energy fuel. Why are they using that instead of a higher energy fuel? Well, we've got the higher octane rating, so I can have higher pressures and higher compression ratios and things like that in our engine. I'll come back and show you that in just a second and how that works. So now the column in the middle here I have labeled as E85. So now when you see this E and a number in here, this is a blend. This means I'm going to blend something together. In this particular case, E is the ethanol, so it's a blend of ethanol, E85, 85% ethanol, 15% gasoline, and the difference between the two. And so the properties are going to fall basically right in the middle. So, and we could scale that. We could actually calculate for different blends what the energy content would be, what the density would be, what the octane would be, and so forth. So it would be kind of a linear scaling in between these two. All right, so that's what those are. That's a blend. Okay, now think about our typical fuel supply. When you go to a fuel pump, almost all fuel pumps, or when you're buying fuel for your automobile, if you're buying gasoline, it's going to be probably a 10% blend of ethanol. So we could actually call that E10. So that's what we would say, that typical gasoline that you buy is E10. Now, we rarely do that because that's kind of like the common supply. That's what everybody gets. But understand that gasoline supply is probably 10% of ethanol. And we do that as an oxygenator. And we're going to come back when we look at some of the stoichiometry and the chemistry combustion reaction. We'll see why that is important, why we have ethanol in there as an oxygenator to put oxygen in the fuel. And that'll be pretty neat when we see that. So it replaces what used to be a methyl tetralbutyl ethylene. It was another additive that we put in gasoline gasoline to give it a little bit more oxygen. This was a petroleum-based additive, and laws and everything said, okay, we can't use that additive. We have to use ethanol and so forth. Now, you can get non-ethanol fuel, and there's some reasons for that. Marine applications, for instance, is very common to have non-ethanol fuel, so you want to make sure your fuel doesn't have any ethanol in it. And part of that has to do with the storage containers. So a lot of boats have aluminum or fiberglass storage containers so that they're lighter, and ethanol likes aluminum and likes fiberglass. I mean, likes in terms of likes it for lunch, so it will can actually damage and destroy some of those aluminum or fiberglass type products and storage containers and so forth. And so in some of those products and some of those applications, we want to make sure we don't have ethanol in it. But a lot of times, most of our fuel, if you just go to a gas pump, you're going to get some ethanol in your fuel. There is some E85 supply available, and if your vehicle has this flex fuel rating, it will be able to burn that 85% ethanol. So it can burn E85. And a little different performance, and we'll show how you can calculate what the performance difference is and so forth in just a minute. But that's what you can have there. Now, all of your vehicles, anything that's reasonably new, is going to be able to handle even more than 10% alcohol and be able to burn that effectively. But E85, unless your vehicle says flex fuel, you don't want to put that E85 in your vehicle. It's not going to run very well. So that's typical spark ignition fuels. Compression ignition fuels, typically basically two different things that we put in there. Now, we do blend some other stuff into these fuels like kerosene and things like that. A lot of that is for a temperature compensation. I'll mention that in a second. But typically, it's number 2 diesel fuel that we buy. What you find actually is there's a lot of variations in diesel supply. So diesel can be a lot of different things. So it's not as tightly regulated in terms of standards as gasoline is. So especially if you're buying bulk on a farm or something like that, that's something that you can work pretty specifically with your supplier to make sure that you're getting exactly what you expect and you have the fuel exactly what you need for your particular climate and so forth. But typical number 2 diesel fuel, the other alternative that we've seen in recent years is this biodiesel. So we convert oils, soybean oil or used cooking oil or whatever into a diesel product, into a diesel fuel. And it has a little bit different properties. Again, a little bit lower energy density, not as big of a difference between diesel and biodiesel as we saw between gasoline and ethanol, but still a difference nonetheless. 129,000 BTUs per gallon versus 118 gallon. Densities are pretty similar, not a huge deal for those things. But here's the other big kicker that we always have to watch is this cloud point right here. Diesel fuels, and any fuel for that matter, will freeze eventually. And diesel, when it gets cold, we commonly say it will gel up. It'll turn to gel. And it literally, actually, when it gets so cold, it will turn to a jello-type material. It'll be a gelatinous mess. So kind of like Crisco, your cooking oils in your home, when it's cold, when you put that Crisco in a pan, it melts and becomes a liquid. And when I take it out of the pan, it will get to be a solid. Some of those cooking oils and lards and things like that on really, really hot summer days, like if you go camping or something like that and it's out in the heat and in the sun, some of those will actually melt. They'll turn to a liquid. Well, it's the same process that's happening with diesel fuel, though we need it in a liquid form. But if that diesel turns into a gel in the tank or in the lines that is moving the fuel from the tank into the engine, it can be a real problem. It just won't pump and the vehicle won't work. So we need to think about managing our fuel supplies of where this stuff gels up and what its cloud point is. It's kind of like its freezing point of the temperature where it starts to get nasty. And for diesel fuel, again, a big range here, anywhere from 5 degrees, and this is in Fahrenheit, up to 41 degrees. So we need to think about that. Biodiesel is a lot worse. So some biodiesels at 50 degrees, a little above 50 degrees, it starts to gel up. So when I'm using biodiesel or any diesel fuel product, I need to think about what kind of additives are in it. So we put different additives in to move that cloud point down to make sure that that material stays liquid at very low temperatures. And depending on the climate where you're using this vehicle, in the southern United States, it's not that big of a deal, but in northern U.S. and Canada, for instance, where we're going to see colder temperatures, it's very common, and I need to be able to use that fuel at very cold temperatures. I need to make sure that it stays flowing even at those very cold temperatures. So those are things that I have to watch and be careful about. So that's the cloud point. Now, the last thing down here on this table is cetane. Oh, so cetane is like octane for diesel fuel, but it's opposite. All right, here we go. So octane, we talked about earlier, is the auto ignition property of the fuel. So the higher pressure and temperature it takes to light that fuel, the higher the octane is. Cetane is exactly the opposite. So the higher the cetane number, the lower the ignition pressure and temperature. So that means that it's going to be easier to burn, which is kind of a good thing. So I want that stuff to ignite based on pressure. So the lower the auto ignition pressure is, the better it's going to ignite, the better it's going to burn. So the cetane goes in the opposite direction. We'll come back to that and look at that specifically, but that's what it is. So see, one of the advantages again of biodiesel, kind of like ethanol, is it's got a much higher cetane rating. It burns easier, so helps my starting and those kind of things. But we'll come back to all that. So most of our biodiesel supply is like a B5, so 5%, maybe B2, something like that. So most of the diesel that you buy at the pump, most of your common supplies is going to have some diesel in it. They are going to have some additives for cold weather, and certain climates you buy winter diesel and summer diesel. So summer diesel might be a little bit cheaper, might have a little bit more energy in it. Winter diesel has those additives to make sure it doesn't gel up. That might affect the energy content and so forth. So those are things that you have to watch. But one of the things that biodiesel does for us, and I'll mention this in terms of diesel supplies, it adds lubricity, it adds lubrication. So as that fuel has to go through the engine, go through an ejector pump and stuff like that, those are a lot of moving parts and very tight tolerances in those injection pumps. And so I got to have some type of lubrication in there. Well, if you go back a number of years, our diesel supply had a lot of sulfur in it. And that sulfur is what gave us that lubricity for the fuel injectors, for the fuel pump, and so forth. Well, sulfur is not good to be burning and blowing out into the atmosphere. It becomes sulfur dioxide. It becomes nasty stuff. And so we said, look, we got to get that sulfur out of our diesel supply. So now we have a challenge of how do I lubricate those parts? Because if I take the sulfur out of my diesel fuel, there's nothing to lubricate it. Those parts are going to wear out, and that's what happens. So what the biodiesel does is it gives us some of that lubricity back. So it's a kind of a pretty good lubricant. And so that it adds some of that lubricity back into the fuel. So that's where we see why we usually have a little bit of biodiesel in our fuel supplies and so forth. So those are the main properties. So we're gonna tear into these a little bit more. We're gonna go back to that energy in just a second. We're gonna look at how that energy affects the performance, how different fuels, how we could expect that to affect the performance of different engines and so forth. So that's where we're going from here.